Imagine being done with GED science. Wouldn't that be a great feeling? Well, if you've always been horrible at science classes and you've always hated science, don't worry. M felt that way too. M was kicked out of high school for attendance issues, but later bounced back and passed the GED in just 3 days, and I want to help you do that too. My name's Parker from Test Prep Champions, and I'm here to help you pass the GED as fast as possible. Now, this one video might be all it takes. If you really understand everything, you might be able to pass just based off of this, but I can't guarantee that. If you're really struggling, then you're probably going to want to study more. It's up to you to decide that. Now let's get started. One more thing, in this video we'll be working out of the study guide written by the official GED testing service. Please see the description below for the link to that study guide. Okay, so the first question says, 2 chemists are designing instant hot and cold packs for a sports medicine supply company. Their design uses chemicals that react with water to either heat up or cool down the water inside the packs. They are investigating the reaction of ammonium chloride with water to determine whether it is exothermic or endothermic. Chemist A read a study done recently by the National Institute for Standards and Testing, which reported that 27.6 kilojoules of energy are absorbed by 100 grams of ammonium chloride when it is mixed with water. And Chemist B measured the temperature of the water in which the reaction takes place before and after the reaction. The results are displayed in the table. So here is the table right here. Now it says measurement, trial 1, 2, 3, 4, 5, and average. And it says here water temperature before reaction, water temperature after reaction, change in water temperature, and then it gives you the values here for each trial. Now the question says, does Chemist B results support or contradict that evidence reported by Chemist A? And you can use the calculator for this question. You have answer choices A, B, C, and D. A says Chemist B's results support Chemist A's data because the reaction gains less energy than the water does. B. Chemist B's results contradict Chemist A's data because it indicates that the reaction gains energy instead of losing it. C. Chemist B's results contradict Chemist A's data because it indicates that the temperature of the reaction should go up rather than down. And D. Chemist B's results support Chemist A's data because the lower temperature of the water indicates the energy is absorbed by the reaction. Now I wanted to read all this out because if you're watching this on mobile or a mobile device like a phone, the text might be kind of small, so I wanted to make sure that I read everything out here, and now I'm going to give you a chance to pause the video, try to figure this one out, and then if you get stuck, don't worry, we'll go over how to get this right. With an endothermic reaction, you should just remember that energy is given off and temperature is going to increase. Now, with an endothermic reaction, energy is absorbed and temperature decreases. Chemist A's study, according to that study, right, energy was absorbed in that reaction of ammonium chloride with water. Well, since energy was absorbed, we can conclude that this was an endothermic reaction. So let's look at the data here. And looking at Chemist B's data, what we see a decrease in temperature in each case. When we look at the water temperature in each trial, and if we look at it before compared to after. So basically, for example, trial 1, we see that before the reaction, the water temperature was 35.4 degrees Celsius. Now, if we look at the water temperature after reaction, it was 12.2 degrees, right? All right, and so basically, if we just look at all the trials and we see the negative signs in front of all of them, that's showing us that there was a decrease, right? In the average, negative 22.9. Now, this is going to match what Chemist A read, all right? So that tells us that D is the correct answer. So I know this is kind of complicated, so I typed out a written solution here. So if you'd like to, you can pause the video, take your time on the written solution, and if not, we can just keep rolling right along. So question 2 says, about 2.7 billion years ago, the lower atmosphere had almost no oxygen. It was before plants existed to produce oxygen. However, in the upper atmosphere, oxygen can be produced when carbon dioxide is split by sunlight into carbon monoxide and oxygen. Scientists examined 11 micrometeorites and all older than 2.7 billion years old, and discovered that most of them had once been particles of iron mixed with oxygen. In order for that to happen, there had to be almost as much oxygen in the upper atmosphere as there is now. The scientists say that the new information about the upper atmosphere does not change what they know about the lower atmosphere. Question: which statement accurately summarizes the passage? A. Micrometeorite analysis proves that 2.7 billion years ago there was no oxygen in the lower atmosphere or the upper atmosphere. B. Micrometeorite analysis proves that 2.7 billion years ago there was oxygen in the lower atmosphere but not in the upper atmosphere. C. Micrometeorite analysis proves that 2.7 billion years ago there was oxygen in the upper atmosphere but not in the lower atmosphere. Or D. Micrometeorite analysis proves that 2.7 billion years ago there was oxygen in both the lower atmosphere and the upper atmosphere. So I'll let you pause the video, take as much time as you need. If you get stuck, don't worry, we'll go over it. Okay, so I'm going to underline a key sentence here, the sentence that says, in order for that to happen, there had to be almost as much oxygen in the upper atmosphere as there is now. So I'm underlining this sentence right here. And I want you to consider this sentence for a second, because from it we can conclude that there must have been oxygen in the upper atmosphere. And why is that important? Well, it's important because it lets us rule out answer choices A and B. Because A says there was no oxygen in the lower or upper atmosphere. Well, this sentence proves there was oxygen in the upper atmosphere, therefore A is false. Okay, so B as well, it says, but not in the upper atmosphere, so B is false, because this sentence tells us that there has to have been almost as much oxygen in the upper atmosphere as there is now. It's a bit of a tongue twister to say this. Okay, so next let's consider the sentence that tells us it was long before plants existed to produce oxygen. And from this sentence, we can conclude that there was no oxygen in the lower atmosphere. Thus, answer C is correct. But here's the thing here. I think that the sentence is, this whole wording here is a little bit tricky, which if you pick D, I don't want you to feel bad about that, because the first sentence tells us that the lower atmosphere had almost no oxygen around 2.7 billion years ago, and the word almost seems to imply here that there was some oxygen, just very little, so that might have led you to pick answer choice D. So if you thought D was the answer for this reason, you were definitely still on the right track, but the official answer key from the GED testing service says C is the right answer, so that's what we're going to roll with here. A little bit of a tricky wording, but that's the answer, and I have a written solution here up on the screen if you want it, if you want to look at it, pause the video maybe, but if not, then we'll keep rolling right ahead. Okay, here's the next question. It says, dissolved carbon dioxide gas, CO2, creates carbonic acid in ocean water. Rising ocean acidity levels may harm marine life. For example, high acid levels may cause hearing loss. Scientists conducted an investigation to study the effect of increased acidity on fish hearing. A group of fertilized fish eggs from the same parents were divided into 4 different aquariums, each with a different pressure of CO2. One tank contained the normal atmospheric conditions of 390 microatmospheres of CO2. The other tank contained 600, 700, and 900 microatmospheres of CO2, respectively. The same number of eggs was placed into each aquarium. The eggs hatched and the fish lived in these aquariums until testing. To prepare for the experiment, one fish was placed into an aquarium containing the same CO2 pressure in which it was raised. The fish's position was recorded every 5 seconds for 2 minutes. Then sounds from the predatory fish were played from an underwater speaker at one end of the aquarium at a volume that was audible to the fish when swimming near the speaker. So the volume was only audible to the fish when swimming near the speaker. The fish's position was again recorded every 5 seconds for 2 minutes. Trials were repeated with fish from each tank. The study showed that fish raised in elevated CO2 levels did not avoid the sounds of the predator fish. They spent approximately the same proportion of time at the speaker end of the aquarium before and after the sounds of the predator fish were played. However, the fish from the aquarium with the normal atmospheric CO2 pressure avoided the speaker end of the aquarium after the predator sounds were played. So it's a lot to fit on screen, but here's the question. What are the independent and dependent variables in the investigation? A. Independent equals CO2 pressure, dependent equals position of fish. B. Dependent equals number of eggs in the aquarium, dependent equals CO2 pressure. C. Independent equals the position of the fish, the dependent equals number of eggs in the aquarium, and D. Independent equals the temperature of the water, and dependent equals the CO2 pressure. So pause the video and work your way through this, or at least try your best, and then we'll go over it. It can't hurt to take a minute or two on any question to just make sure you really understand what's happening in the experiment. Now, I don't want you to take forever on your test and trip up on every little detail, but if you're having trouble with a question, you might want to just go back and make sure you really understand it. So here, basically, the researchers took the fish eggs from the same parents and put them into 4 different tanks. Now, each tank had a different pressure of CO2. Right, 390, 600, 700, and 900. They put the same number of eggs into each aquarium, and the fish hatched and stayed in their aquariums until testing. So that was kind of the pre-work they did before the actual experiment. Next, what they did was they put a fish in a tank with the same amount of pressure it was raised in. Now, they recorded that fish's position every 5 seconds for 2 minutes. So in case 1, that's what this is representing here. And so this little dotted arrow, I just kind of put that in here to illustrate that they're recording the fish's position every 5 seconds for a 2-minute duration. So that's like they put a timer on for 2 minutes, and every 5 seconds they're recording where it's going to go. So next, they put a speaker at one end of the tank, and here's my beautiful speaker right here. And the speaker played a predator fish sound. And they did the same thing. They recorded the position again every 5 seconds for 2 minutes. They then tested all the fish with the speaker in the tank. Okay, so I drew arrows on the screen because I know there's a lot happening here to this little blurb I typed out right here for you. And it's basically just teaching you about the definitions of a dependent variable and an independent variable. This is kind of a confusing concept, but I just want to make this as simple to understand as possible here. All right, and so in an experiment, there's an independent and a dependent variable. The dependent variable depends on another variable. The independent variable does not depend on another variable here. Okay, so right away, if you saw that this question had to do with independent and dependent variables and you didn't know these definitions and you've never heard this concept before, you might have had trouble answering this question right off the launching pad. But I just want to point out here that you might have still been able to eliminate B and D without knowing anything about the dependent and independent variables. So let me explain why, right? If you look at B, we know right off the bat that B is wrong because the number of eggs was the same in each case. So it really just goes back to, remember how I showed you those pictures of my kind of illustration of what was going on? It just goes back to understanding the details of the experiment here. And we can rule out B just off of that because the number of eggs, it didn't change. It's not a variable because it was the same in each case. And also D here, note that the temperature of the water was not even mentioned in the passage as being relevant to the experiment. So considering that the temperature was not relevant here, we could also take D out. So recall that the scientists found that the fish raised in higher CO2 did not avoid the sounds, but those raised in normal CO2 did. Now, whether or not the fish avoided the sounds from the speaker, in other words, the position of the fish, it depended on the pressure the fish were raised in. And since the position of the fish was dependent on the pressure, the position of the fish is the dependent variable. And the CO2 pressure is the independent variable. So A here is the final answer. All right, and so here's the solution here. If you had trouble with this, go ahead and take your time. Make sure you read this. Just kind of let it sink in. I know it can be kind of confusing here. But whenever you're ready, we'll go right ahead to the next question. Okay, question 4, and thank you for sticking with me this far into the video. Question 4 says, a small woodland ecosystem consists of plants and small brush, rabbits, chipmunks, mice, and hawks. And we've got a nice diagram right here on the screen. Now your question, based on this simplified food web, what would most likely happen if a coyote were introduced to the ecosystem? A, the hawk population would increase. B, the mouse population would increase. C, the plant population would decrease. Or D, the rabbit population would decrease. So let's have you pause the video, try to reason your way through this, and then we'll go over it. Okay, so the way to think about this is you have to see that there's a hierarchy here, right? So the top of the hierarchy, I'm going to just call this tier 1. At the top are the coyotes and the hawks. Now, in the second rung here, we see the mice, chipmunks, and rabbits, and I've labeled that rung as number 2. And the lowest on the totem pole is 3, which would be plants and small brush. So let's go through A, B, C, and D and just kind of common sense our way through this, right? So answer choice A. If we add coyotes in here to the ecosystem, is the hawk population going to increase or is it going to decrease? Well, think about it. If there's no coyotes here and the hawks are going to feed on the mice, chipmunks, and rabbits because the hawks are higher up in the food web, the hawks are going to have the mice, the chipmunks, and rabbits all to themselves until we put the coyotes in. So the coyotes are then going to compete with the hawks. So if the coyotes start eating up more mice and chipmunks and rabbits, there's going to be fewer available for the hawks to eat. The hawks aren't going to get as much food. Some of the hawks are going to starve and aren't going to make it, unfortunately, for the hawks. And therefore, A is false because, if anything, we would expect to see the hawk population decrease because the coyotes are going to come along and eat more of their food. B, the mouse population would increase. True or false, basically. Is it false or is it true? Well, think about it. Coyotes are higher in the food web than the mice, which we can therefore see means coyotes are going to be eating mice. And if we put coyotes into the ecosystem, more mice will be eaten, so B is simply not true, so we'll cross it out. Now what about C? Well, the thing here is that C is also wrong, and the reason is because there's no evidence that introducing coyotes is going to cause the plant population to decrease. Now, if anything here, we could in theory say that the plant population is going to be more likely to increase here. Now, why would that be the case? Well, think about it. Mice eat plants, chipmunks eat plants, rabbits eat plants. If the coyotes come along and start devouring more mice, chipmunks, and rabbits, there's going to be more plants. So if there's more plants, then why would the plant population decrease? Well, if anything, I would say that the logical conclusion is that it's going to increase because there's fewer mice, chipmunks, and rabbits to eat the plants with the coyotes around. Okay, so what about D? Well, the rabbit population, well, D is actually the last standing survivor here, so D is right, but we know that the rabbit population is simply going to decrease because if coyotes eat rabbits and we don't have any coyotes around, but then we put coyotes in, they're going to eat more rabbits, the rabbit population is going to decrease. All right, so I went over this a little bit fast. This is not that simple. I might have made it seem like it's more simple than it really is. So here's the written solution. You can take your time reading it. Okay, the next question. Carbon-14 is a radioactive isotope of carbon that decays at a known rate. Plants take in both carbon-14 and carbon-12 to use for photosynthesis. However, when the plant dies, it can no longer take in carbon, and over time the radioactive carbon-14 decays while the carbon-12 remains. This process results in the ratio of carbon-14 to carbon-12 decreasing. By measuring the amounts of carbon-12 and carbon-14 in a sample, it is possible to determine the age of the sample. The age of the sample is inversely related to the amount of carbon-14 present in the sample. Since some tree species live for thousands of years, it is possible to count the annual tree rings to determine the accuracy of radiocarbon dating by measuring samples removed from a particular ring in a tree. In the graph, the dots represent the comparison of one sample measured with both carbon-14 and tree ring dating. The line represents a match between the two measurements. So the actual question says, while the two age measurements agree for more recent dates, they often do not agree for samples dating back more than 3,000 years. Scientists attribute most of this deviation to changes in carbon-14 production caused by changes in Earth's magnetic field. Which statement correctly analyzes the observed deviation? A. Radiometric carbon ages are too low, implying that less carbon-14 was present. B. Radiometric carbon ages are too high, implying that less carbon-14 was present. C. Radiometric carbon-14 ages are too low, implying that more carbon-14 was present. And D. Radiometric carbon ages are too high, implying that more carbon-14 was present. And we can see the graph over here on the right hand side of the screen. So as always, I'd like you to pause the video and then we'll go from there. Okay, so really what's going on here is that there are two different methods for measuring the age of a sample. There's the radiometric carbon method, which is detailed here in the first paragraph. And then the other method to age the sample is the tree ring dated method, which they describe right here in the second paragraph. And so what they're showing on the graph, first of all, they're using the scatter plot to represent the data. And the red line is called a line of best fit. And the line represents a perfect match between the two measurements. So when we look at the graph here, we'll see that on our y-axis, we have the results of the carbon dating. And on the x-axis, we have the results of the tree ring method. What you have to understand is that the red line here represents what the results would look like if there was a perfect match between the results of the two different methods. So in other words, if they got matching results from both methods, all of the data points would be on the red line. For the first 3,000 years or so let me highlight this on the graph. So maybe I'm just estimating this. So let's say here, everything to the left of this black line. All right, so everything over here to the left of the black line, let's let that represent the results of the first 3,000 years. What we note here is that all of the data points, for the most part, are either on the red line or they're very close to it, right? There's a couple that are off of it, but for the most part, the dots are either on the red line or very close to it. So what that tells us is that for the first 3,000 years, the results of the carbon dating method and the tree ring dating method, they matched very closely. So after 3,000 years though, which would be everything to the right of this little black line I drew, everything over here, we note that almost all of the dots are below the red line, and quite a bit below the red line too. And so what you need to understand here is that values below the line are less than the predicted value. So again, the red line predicts what the values would be if there was a perfect match. Since all of these values here are below that red line, okay, that tells us that we know that the radiometric carbon ages are too low, all right? And so really we can rule out D and B just based off of that, because again, we have to look at the Y values here. So the Y values are all below this red line, tells us that the data points are below the predicted values as given to us by this red line. And the other piece to the question here though that I want you to think about here is this line here where it tells us the age of the sample is inversely related to the amount of carbon-14 present. So what this basically means is that the greater the age, the lower the amount of carbon-14 present, and the lower the age, the greater the amount of carbon-14 present in the sample. All right. So if radiometric carbon ages are too low, which we've already determined that they are, that would imply that more carbon-14 is present based off of the factoid here that they've given us at the end of the first paragraph. So this is actually a really confusing question. I would say this is one of the hardest ones on this test. So I'm going to put up the written solution, and if you had trouble with this, just please take your time. You could rewatch the explanation or just study the written solution here. Then when you're ready, we'll move ahead. Okay, so the next question says, a temperature change occurs when ammonium chloride is dissolved in water in a water solution. The table shows the temperature change over a period of 120 seconds. And we see in the table there's time and seconds. We've got 0, 30, 60, 90, and 120 seconds. Then we see temperature in degrees Celsius is 21.1, 19.4, 18.8, 18.3, and 17.7. And there's a formula given to you right here, and the formula is Fahrenheit equals degrees Celsius times 9 over 5 plus 32. And the question says, what is the appropriate temperature of the solution in degrees Fahrenheit at 60 seconds? You may use a calculator. And I put the answer choices up here just because I was running out of room on the screen here, so that's why the answers are right here. So you know the drill by now. Thank you for sticking with me here. I'll have you pause the video, give this a try, and then as always, we'll go over it. All we have to do here is we want to check at what the temperature is at 60 seconds. So on the table at 60 seconds, the temperature in degrees Celsius, it's 18.8. And so we want to convert this into Fahrenheit. So I'm going to use the formula here, and I'm going to replace the letter C here with 18.8. If I do that, this is what it's going to look like. So 18.8 times 9 over 5 plus 32. And fortunately, we are able to use our calculator for this question. So the fast way to do it, oops, that should be a plus sign. The fast way to do it would be to just throw this in your calculator. And if you do that, you're going to get a number that rounds to 66. And D is the correct answer here. Now, I want to share with you two quick tips here. And you can memorize these. It might save you some time for a temperature conversion on the test, but you don't have to memorize these. You can also use the formula. But basically, the quick way, if you have to go from degrees Celsius to Fahrenheit, is you just you multiply the temperature in degrees Celsius by 1.8, then you add 32. And to go from Fahrenheit to Celsius, you would just take the degrees Fahrenheit, subtract 32, then divide by 1.8. Now let me show you the written solution. You can take your time with this, and then when you're ready, we'll move on. Okay, so the next question says, a set of parents want to determine the likelihood of the eye color of their offspring. The parents know that their genes for eye color each have 2 alleles. The alleles are represented by letters in the form of a genotype. One parent has a genotype of b with brown eye color, and the other parent has a genotype of b with blue eye color. Their offspring will inherit one allele from each parent. Question: what are the possible genotypes of their offspring? A, 100% big B, little b. B, 100% little b. C, 50% big B, 50% little b. Or D, 25% big B, 75% b. So let's have you pause the video and give this one a shot. And as always, if you get stuck, don't worry. I'll make sure that we go over how to do it. Okay, so to get this question right here, we're going to use a tool called a Punnett square. And the idea here is that there are two different alleles here. There's the big B allele and the little allele. The child is going to end up with two alleles. There's going to be one allele given from the dad and one allele given from the other parent, all right? So in this case, let's say that the dad has the blue hair. Blue eye color, not hair color. And so the dad has one little b allele and another little b allele. So the dad's unique combination of two alleles is little b, which is blue eyes. And the combination, simply put, the combination of alleles is what we call the genotype. Now let's say that the parent with the brown hair is mom. So if mom has brown hair, what is her unique combination of alleles? Well, she has a big B and a little b. The child can get one big B allele from mom, and that big B allele from mom can combine with the first little b allele that the dad has, or that big B from mom, that big B allele from mom can combine with the other little b allele that dad has. Or the mom can contribute a little b and dad can contribute a little b. Mom can contribute that little b, and the other little b allele that dad has can also combine with the mom's little b allele. All right, so I know that's kind of a tongue twister, but this is all the different possible combinations. So again, all I did was I just lined it up here. I took the dad's two alleles, the little b. I took the mom's two alleles, her big B and a little b, and I just wrote out all the different combinations of alleles. So I took the big B, the little b, I took the big B from mom, put it down here, the little b from dad, put it right here. I did the same thing with the little b's, all right? So I took a little b from mom, put it here, little b from dad, put it here, little b from mom, put it here, little b from dad, put it here. All right, so hopefully that makes sense. I know it's a little confusing, but we now have to figure out the percentages. And it's pretty easy here. So basically half of the offspring are gonna inherit the allele combination big B, little b. So 50% are gonna get the allele combination big B, little b, and 50% are going to get the combination little b, little b. So that corresponds to C. And so I will put the written solution right here for you. Take your time. It's a little bit tricky, all right, but this is important to understand. All right, the question says, a scientist was investigating if differences in the frictional work performed on a model car can change depending on its mass in grams, and whether the car moves up or down an inclined plane. They decided to measure the amount of frictional force experienced by the model car and the distance it traveled in meters. The scientists were able to evaluate the frictional work using the following data. And the chart says mass in grams, distance, force, and work done by friction. It says car going up the incline, and it says 100, 39, 0.063, 2.457. Then it says car going down the incline 70, 39, 0.2309. It is known that the relationship between force and distance determines the work done by friction, W little f, and it says that the work done by friction is equal to F times D, where F is force and D is distance. And the question says how much work done by friction was exerted on the car as it moved down the inclined plane. So as always, you can pause the video. Let's try this out and then we'll go over it. Okay, so they give us the formula here. We're going to use work done by friction equals F times D. And basically we already know for the car going down the incline that the force is equal to 0.2309. So that is the force. And we fortunately also know the distance, which is 39. And we know that the work done by friction is equal to the force times the distance. And here they've given us a lot of information that we don't need for the question, so you don't need to do anything at all with the mass. You don't need to do much with this going up the incline. I should say you don't have to do anything. And the answer, if you put this in your calculator here, you're going to get an answer that rounds to B, right? So you should get something that's about 9.005, depending on how your calculator rounds it, but B is the correct answer.